Welcome, my friends. Consider the two inequalities 2x plus 4 is less than 2 or 4x minus 1 is less than negative 25. We begin by solving each inequality separately for x. For the inequality on the left, we subtract 4 from both sides to get 2x is less than negative 2. Then we divide by 2 to get x is less than negative 1. For the inequality on the right, we add 1 to both sides to get 4x is less than negative 24. Then we divide by 4 to get x is less than negative 6. Now remember that these two inequalities were joined by an OR statement, which is important for how we will write our solution. The most important way to visualize our answer is to look at a number line. Here is the graph for x is less than negative 1 on a number line. It includes the values for x that are less than negative 1, but do not include negative 1, indicated by the open circle at negative 1. Here is the graph of x is less than negative 6. Since our two inequalities are joined by an OR statement, we need the solution that includes the area in either the first or the second graph. Another way to think about it is that the solution contains all numbers that are shaded in either of the two graphs, which in this case is simply x is less than negative 1. X is less than negative 1 is the least restrictive and includes the shaded area in either of the two graphs. Oftentimes you will see the answer represented in interval notation as parentheses, negative infinity, comma, negative 1, close parentheses. This indicates that our solution set starts at negative infinity and can include values up to but not including negative 1, indicated by the parentheses. Let's try this example. 3x plus 6 is greater than 12, and negative 2x minus 4 is less than or equal to 2. Just like before, let's solve each inequality individually for x. Subtracting 6 from both sides of the left inequality, we have 3x is greater than 6. Dividing by 3, we get x is greater than 2. Adding 4 to both sides of the right inequality, we have negative 2x is less than or equal to 6. Dividing by negative 2, we get x is greater than or equal to negative 3. Remember that when we divide or multiply an inequality by a negative number, we must flip the inequality sign, which is why the less than or equal to sign switched to a greater than or equal to sign in this step. Let's create the number line for each of our solutions. Here's the graph for x is greater than 2. We have an open circle at 2 to indicate we are not including the number 2, since we have a greater than sign. Here's the graph of x is greater than or equal to negative 3, which has a closed circle at negative 3 due to the greater than or equal to sign, indicating that we should include the value negative 3. Now, unlike the last problem, these two inequalities are joined by an AND statement. AND means that our solution must be common to both the first and the second inequality. The area that is common to both inequalities is that of x is greater than 2. X is greater than 2 includes the area common to both the first and the second inequality. Expressing this in interval notation, we have parentheses 2, comma, infinity, close parentheses, meaning our interval contains any values that are greater than 2, all the way up to infinity. Let's try another one. We have 2x minus 3 is less than 3, or 3x plus 1 is greater than or equal to 19. Adding 3 to both sides on the left inequality, we have 2x is less than 6. Dividing by 2, we have x is less than 3. Subtracting 1 from the right inequality, we have 3x is greater than or equal to 18. Dividing by 3, we have x is greater than or equal to 6. Here is the graph of x is less than 3. Here is the graph of x is greater than or equal to 6. Since our statements were joined by an OR statement, our solution is the area that is part of either the first or second graph, which looks like this. Since this is not a single continuous interval, we express this as the union of two separate intervals. The first interval goes from -infinity all the way up to 3. The second interval begins at 6 and goes up to infinity. We use a bracket on the 6 here to indicate that 6 is part of the solution, as we had a greater than or equal to sign and a closed circle on our graph. We use the union symbol, which looks sort of like a capital U, in between our two intervals to indicate that the solution contains values inside either of the two intervals. Now, notice that in this case, if our two inequalities were joined by an AND statement, there would be no solution. Here's the same problem worked out with the AND statement in the middle. We still have the same two graphs, but notice that there is no area in common on our number line. There is no area that is part of the first graph and the second graph. So the solution to the same two inequalities joined by an AND statement is no solution, which we represent by an open circle with a slash through it, which we call the empty set. There is one more case you could come across. Saving the algebra, let's say we worked out a problem and it came to x is less than or equal to 3, or x is greater than or equal to -4. Here's what the number line would look like for each inequality. Recall that for an OR statement, the solution is what is included in either the first or second inequality, which in this case is the entire number line. For this case, our solution is all real numbers, which we write as -infinity to infinity in interval notation. Alright, my friends, that completes our video discussing solving compound linear inequalities using interval notation.